Welcome back. Today we are breaking down the different types of numbers. They can be also referred to as number systems. We are going to break them down fast, clear, and in a way that prepares us for higher mathematics. In our last lecture, we asked ourselves, what is a number? Today we answer, what kind of numbers exist? And ask yourself, why do we need them all? The first number type is natural numbers. These are the counting numbers. We have them starting from 1, 2, 3, and so on. Their historical need was for counting, trading, and survival, and be denoted as n, which is n referring to 1, 2, 3, 4. The next type of numbers is the whole numbers. The whole numbers came from natural numbers. And what was the innovation from coming from natural numbers? That was adding 0. Why was it revolutionary? The concept of nothing as a quantity. Whole numbers can be denoted as W referring to 0 and so on. The crisis that came, what if you owe more than you own? What if you are demanded more than what you have? Then that introduced integers. The problem was to be answered by introduction of negatives. The problem, for example, 5 minus 7. The solution was adding a negative. The solution was introduction of negative numbers. As you can visualize on the number line extending left of 0. Integers can be denoted as z, as you can see, but there came the ratios, the solution, and the betrayal. What if numbers were expressed as ratios? That introduces us to rational numbers. These are numbers that are expressible as fractions. I think we are seeing that on our right hand side, the number family is getting bigger. We have natural numbers, whole numbers, integers, and Roman numerals. Numbers expressible as fractions are rational numbers. For example, a over b, where b is not equal to 0. For example, 3 over 5. The property, they had properties. The property was their decimal expansion either terminates or repeats. What is termination? Termination, for example, 0.75, negative 5, negative 2.4. In this case, it means the decimal number has a limit where it stops. And then what is repetition? Repetition, for example, 5 over 6. If it is expressed as a fraction, it has a repeating pattern. And then we also have 0.333. It means 3 continues up to the end. Rational numbers can be denoted as Q, as we are saying, open brackets a out of b, where a and b are both integers, but b shouldn't be equal to 0. These numbers made a promise. In inversion, they made the promise that all numbers are rational. All numbers should be the rational. But remember, we said a solution and a betrayal. And what was the betrayal? The betrayal was the discovery, the Pythagorean discovery of root 2. The Pythagorean discovery of root 2 that introduces us to numbers that are not rational, which are irrational numbers. These are numbers that cannot be expressed as fractions. For example, root 2. Other examples, root 2 is a surd. Other examples, we have pi, e, root 3, and so on. Then we complete the continuum and beyond. We add all these numbers and we give them a name. These are real numbers. Real numbers come after the unification of rational and irrational numbers. I think you are seeing that the family is getting bigger. We have natural numbers, whole numbers, integers, rational numbers, and real numbers. The family is getting bigger and bigger. Every point on the number line corresponds to a real number. And real numbers is the combination of rational and irrational numbers. Then the final crisis. What is root of negative 1? Root of negative 1. That brings us to the final crisis. Then that introduces imaginary numbers or complex numbers. Root of negative 1 is a complex number. And I think you're seeing that the family is getting bigger and bigger. Have natural numbers, whole numbers, integers, rational numbers, real numbers, complex stroke imaginary numbers. The numbers types are 7. The number types are 7. Then the solution is to find a denotation for root of -1, and the solution defines I as root -1. Solutions, for example, can be root of -3, can be I root 3, or root 3I, and root of -9 is 3I. And there comes, are these real? Do they have real applications? Of course, even though they are imaginary numbers, they do have real applications. They are used in electrical engineering, quantum mechanics, and signal processing. Mathematics doesn't invent new numbers arbitrarily. Each expansion solves a concrete problem the previous system failed to handle. We don't have 7 different types. We have one evolving system that gets more powerful with each crisis. So keep up with me, and we transit to another video, the video that really explains properties of numbers. After understanding what a number is, the different types of numbers, then we look at the properties of numbers. Thank you.